Hello, my name is Steve Burt. I'm the team lead for the Economic and Policy Assessment Group at the Institute for Transportation Research and Education at North Carolina State University. I will be providing a demonstration of the cost tool that we developed as part of NCDOT Research Project 2020-44, with the goal to better estimate the comprehensive cost of rail incidents in North Carolina. The cost tool accompanies a research report, the comprehensive cost of rail incidents in North Carolina. The report documents the methodologies used to appraise the various cost elements that are born from railroad incidents. In addition, the report provides an estimate of railroad costs over the last decade in North Carolina, with a detailed accounting of costs for year 2019. The cost tool that I will be demonstrating was used to estimate the values found in this report. I will be demonstrating how to estimate delay, rerouting, and supply chain costs resulting from rail incidents. There are a variety of delay, rerouting, and supply chain costs stemming from rail incidents resulting in delay. Value of time costs accrue for train passengers and crew members experiencing delay. The U.S. Department of Transportation conceptualizes travel time as having negative demand. This is because consumers are willing to pay more to spend less time traveling. The costs incurred from experiencing additional travel time adhere to three principles. First, time expended on travel could be dedicated to production, yielding a monetary benefit to either travelers or their employers. Second, it could be spent in recreation or other enjoyable or necessary leisure activities which individuals value and are thus willing to pay for. Third, the conditions of travel during part of a trip may be unpleasant or involve tension, fatigue, or discomfort. Reducing the time spent while exposed to such conditions may be more valuable than saving time on a more comfortable portion of the trip. These principles underlie the distinctions among value of time recommendations in USDOT's benefit cost analysis guidance. USDOT's value of time estimates are used in this cost tool. Shipper costs are experienced by businesses waiting to unload or receive cargo that has spoiled, deteriorated, or has lost a portion of its useful life. Railroad shippers incur inventory devaluation costs associated with delay. Every product has a useful life, either because it is perishable or because it becomes obsolete. The longer it takes a good to arrive at the destination where it can be used, the less of that useful life is available for the end consumer. Different type of products have varying useful lives and therefore different discount rates. For example, gravel could have a low discount rate because an additional day in transit would not have much effect on its useful life. However, it would affect the shipper's ability to sell it. The research team used the appraisal methodology of Winston and Shirley to estimate shipper costs associated with rail delay. This methodology is implemented in the National Cooperative Highway Research Program Report 755 and the research of Lovett et al. Cargo replacement costs accrue above and beyond shipper costs incurred from cargo loss of useful life and spoilage. These costs are applied to the specific cargo units within the train cars that have been badly damaged during a rail incident. Replacement costs are a direct function of the severity of a crash and secondarily the fragility of the freight. As a general rule, cargo replacement will occur when 1, there is both substantial damage to rail cars, and 2, affected goods are manufactured products or perishables. This is in contrast to bulk commodities. National Cooperative Highway Research Program Report 755, North Carolina Waybill data, and the Bureau of Transportation Statistics Commodity Flow Survey forms. These are the basis for the appraisal methodology and values used for cargo replacement cost appraisal in the tool. Similar to an automobile, train cars and locomotives are subject to wear and tear, fuel, and financing costs. The greater amount of time that train cars and locomotives are in use, the greater the operating costs. Lovett et al. Estimate rail operating costs for locomotive ownership, leasing, and fuel, as well as the cost for operating other rail cars. Their research findings are used to estimate rail operating costs. When trains are delayed, they produce more locomotive emissions because they are on the railway for a longer duration of time. Based on locomotive runtime, and USDOT emissions guidance, Lovett et al. Estimated the emissions cost for an average hour of locomotive operation. Research findings from Lovett et al. Are used to appraise emissions costs. Rail incidents that result in substantial delays may impact rail movements upstream and downstream. For example, severe incidents may require substantial emergency management and cleanup activities that close the tracks to other scheduled train movements. Incidents may also lead to trip cancellations or require train passengers to be rerouted via buses. There are 4 primary categories of upstream and downstream costs for passengers and freight trains that are accounted for in this tool. 1, passenger and crew values of time costs imposed for the next scheduled passenger or freight train as it waits for tracks to be cleared. 2, delay in operational costs imposed for rerouting passengers via bus. 3, delay in operational costs for canceling passenger train trips. And 4, cargo delay and rerouting costs imposed for next scheduled freight trains. Now that you've been briefed on delay, rerouting, and supply chain costs, let's demonstrate how the tool can help estimate them. Delay, rerouting, and supply chain costs are estimated using multiple sections of the tool. In general, these costs are broken into 2 main groups: cost experienced by passenger train crew members and passengers, and cost experienced by freight train crew members and costs associated with cargo. Costs are divided categorically. The red color-coded section of the tool is used to estimate the value of time costs for passenger trains. It accounts for value of time costs for crew members and passengers. The light red color-coded section estimates the upstream and downstream costs that a passenger train incident may impose. The blue section estimates the value of time costs for freight train crew members. The light blue section estimates shipper costs that may result from a freight train incident. The gray section estimates the cargo replacement costs that may result from a freight train incident. The powder blue section estimates upstream and downstream costs that a freight train incident may impose. The dark blue section estimates railroad operating costs associated with delay for passenger train incidents. The blue section estimates railroad operating costs associated with freight train incident delay. The dark purple section estimates the emissions costs associated with delay for passenger trains, while the light purple estimates emission costs associated with freight trains. As you can see, the tool can be used to estimate a comprehensive suite of delay, rerouting, and supply chain costs. All right, let's have a demonstration of the tool. Let's imagine a hypothetical scenario where there's a freight train derailment that takes 3 hours to clear. We're going to assume that there were 2 locomotive engineers on board that experienced no injuries. So first, we're going to navigate to part 3, the section of the tool that deals with delay, rerouting, and supply chain costs. Now, if we remember the red section of the tool, this is associated with passenger train incidents. We want to navigate to the part of the tool that's associated with freight train incidents. We're going to scroll down. And here we are, starting with blue. And this is associated with freight train events. We're going to begin with value of time. We know that there was a 3-hour delay. So we're going to input that as a custom value. Instead of inputting in hours, our tool actually inputs in minutes. So we can go ahead and we can put 60 minutes in an hour times 3 hours. Okay, we have 180 minutes. Now we want to put the type of personnel that's affected. We had 2 locomotive engineers. We don't know their earnings rate, so we're going to just assume they're earning the median salary. And again, there were 2 individuals. So now we've tabulated the value of time costs associated with this 3 hours of delay. Next, we need to estimate any shipper costs that may have resulted from this incident of a 3-hour freight train delay. So there are some values that we need to know related to cargo. First is the value of freight cargo per ton. We're going to go ahead and use the default value here. The value of freight cargo per ton, this really is talking about commodity mix, or the different commodities that are being moved within the freight cars on the freight train. So the opportunity here is to either use the default, or we can go ahead and scroll to the right and see some of the other benchmark values that are available to us. Generally speaking, trains transporting raw materials will have a lower commodity mix value per ton, while those carrying manufactured goods will have a higher commodity mix value per ton. This cost tool includes commodity mix values based on those provided in the National Cooperative Highway Research Program Report 755, the North Carolina Freight Plan, a sample of North Carolina waybill data, and North Carolina statistically expected values of commodity mixes based on their percentile thresholds. So here are some of the benchmark values that we can use, and we're going to go ahead and use that default value. Similarly, we're going to use defaults for freight tons per carload, freight carloads per train, and our total minutes of cargo delay. We want to always have this match the delay that we input earlier, unless there's a specific reason for doing otherwise. And then we want to use the default discount rate. Similarly, we have other options for discount rates based on the commodity mix. So if it's a train that's carrying a high level of perishable goods, we probably want to use the perishable discount rate. If it was carrying a high amount of bulk goods, we probably want to use the bulk. Or if other, we could use other. In this instance, we're going to assume that we don't really have a lot of good information on what type of commodities are being carried. So we're going to use sort of the default or the expected value. Next, we want to go ahead and look at any sort of costs associated with replacement or damage of destroyed cargo. In our freight, this is where we would need context for the type of freight incident that occurred. Because we're going to assume we don't have that context, but we're going to assume that there was an incident that resulted in some sort of train damage. So because of that, we're going to go line by line and use the defaults. Value of freight cargo per ton, we want to use the same input value that we used before. Freight tons per carload, same as before. Damaged freight cars per incident type. Now, this is where if we had specific information, if we knew, okay, there was one freight car carrying cargo that was damaged, we could put that in here. Since we don't know, we're going to go ahead and use the default value. Default value says that in any expected event, there would be 2.63 damaged train cars that are carrying freight. And we're going to use the default for cargo useful life remaining. Now, in the next section, we would want to look at if that 3-hour delay event has any upstream effects or downstream effects. So are there any freight trains that are being delayed at other parts of the system as a result of this event? We're going to go ahead and assume yes. There's going to be the median level of delay, which is 26 minutes upstream or downstream. We're going to assume the default number of crew members on that passenger train, as well as their standard value of time. Also going to assume the same defaults for the cargo that they're carrying. And it's important to note, you'll see that we only really have the value of time for the crew being delayed upstream. And that's because upstream and downstream shipper costs are only tabulated if the incident affects, the incident imposes a delay more than 60 minutes. Next, we have additional railroad operating costs associated with delay that we'd like to estimate. We're going to choose the section designated for freight train incidents. We're going to use the default values for locomotive ownership and leasing, locomotive units, locomotive fuel costs, other train car costs, and we're going to use the 180 minutes of a delay that was experienced as part of the incident. You want to look at the benchmark values. You can see that for our defaults, locomotive ownership is about $30 per hour or 50 cents per minute. Locomotive leasing is about $76 per hour or $1.27. Locomotive fuel costs about $210 per hour or $3.52 per minute. And other train car costs are about 66 cents per minute, or excuse me, 66 cents per hour or about 1 cent per minute. And we have about 2.3 locomotive units per freight train. Next, we can estimate additional emissions costs from the incident. We're going to choose the section designated for freight train incidents. We're going to use the default values for additional idle or running time, the number of locomotives per train, carbon dioxide costs, nitrous oxide costs, and particulate matter costs. And we're going to use the 180 minutes of delay that we experienced as part of the incident. If we look at our benchmark values, we can see our emissions costs per minute. Now we've gone through the different costs associated with delay, rerouting, and supply chain for a freight train incident. Now, if you remember, we talked about the opportunity to customize a delay, rerouting, and supply chain incident as it pertains to commodity mix. So let's go ahead and show an example of how that works. We can navigate to the Freight Cargo tab either by clicking on it at the bottom of the worksheet or by using this shortcut. You are now looking at the commodity mix table. This table was built using a sample of weighable data from Class 1 railroads in North Carolina. The recommended values can be altered to reflect a commodity mix of the cargo being transported. It is recommended to use the default commodity mix values unless you have a specific reason for doing otherwise. However, for this situation, let's assume that we have some information that says we should alter our commodity mix. We can say that we learned that the train transporting cargo is transporting fewer chemical products and more miscellaneous mixed shipments than what is typical. So let's go ahead and find our chemical products. And instead of using the recommended value, we're going to switch. We know that we have fewer of these products being transported. Now, we also know that we have more miscellaneous mixed shipments than what is typical. So let's go ahead and find that. And now we're going to alter this recommended value to a high value. If you see down here, our commodity mix value or our value of freight cargo per ton has been changed. We can use this new value to help with our estimate when looking at cargo costs. So we're going to go ahead and return to the main page. And instead of using that default value for our commodity mix, we're going to use a custom value. And we can remember that that's $2,820 and input that here. So now you've seen how shipper costs can be altered using the freight cargo tab to allow for customization of commodity mix. And remember, commodity mix, that looks at what type of cargo is being transported on a freight train.